So we're here at the example table, and in this video we're going to be looking at more iterated integrals. In particular, iterated integrals over non-rectangular regions. So let's start with this example. The first thing to notice is that the upper limit of integration with respect to x is y. It's not constant. The limits of integration for y are constant. Y is going from 1/2 to 1 over the entire region. X, however, is going from 0 to y. This upper limit is changing. This means that the region over which we're integrating isn't a rectangle. It's actually this region. We see that x is starting at 0, which is the y-axis, and it heads over until it hits y, which is the line x equals y. Y is going from 1/2 to 1, which goes from here to here over the entire region. So we have this quadrilateral, non-rectangular region over which we're integrating the function 8xy. So to see what we need to do to integrate this, well, we go about this in the same way except as we would over a rectangular region, except now we have a y as the upper limit. So we take an antiderivative of 8xy with respect to x, so we get 4x squared y, and we evaluate that from x equals 0 to x equals y. This entire thing is the integrand of this integral, so we have a dy here. Well, we know it's going this expression is going to disappear when we evaluate it at x equals 0, so we're left with the evaluation at x equals y, and when we plug in x equals y, we get 4y cubed. So this becomes 4y cubed dy. And we have from this y to the 4th evaluated between 1/2 and 1, which gives us 1 minus 1/16, or 15/16. Let's look at a second example. In this example, we're going to find the area under the function, actually let's not call it f, let's be explicit, let's call it z. So we're thinking of this as a graph in three-dimensional space. Z equals 8xy, the same function as before, over the region defined as follows. So it's the set of all points xy such that y ranges from 0 to x, and x ranges from 0 to 1. So the difference here is that we need to determine ourselves the limits of integration. In this case, unlike the previous one, y is the variable that has the changing bound. Y is going from 0 to x. So let's integrate 8xy with respect first to y. So we get dy, and y is going from 0 to x. So these are our limits of integration for y. And then we integrate with respect to x. X is going from 0 to 1. And we evaluate this the same way we evaluated the previous example. So we antidifferentiate this with respect to y. So we get 4xy squared. And then we evaluate this from 0 to x. This entire thing is the integrand of this integral with respect to x. When we let's be explicit. This is y equals 0 and y equals x. So when we evaluate this at y equals 0, this expression disappears. We are left with the expression that results when we evaluate y equal to x. So we get 4 times x cubed. So 4x cubed dx, and this is x to the 4th. We evaluate between 0 and 1, and we get 1.